Hi, in this video, I want to show an example of why the slope field is really important. The reason why I bring this up is this. In a typical intro to differential equations class, slope field is taught first, and then after that, you're taught multiple methods of solving differential equations. And in the course of doing that, a lot of people lose sight of how important the slope field is and don't realize that a lot of times in real life, you need to double check your analytical answer or numerical answer with the graphical answer. And this is an example why. Solve the initial value problem. Y prime equals 3y to 2/3, and the initial value is y at 0 is equal to 0. By the way, the point of this video could be made with a simpler equation such as y prime equals square root of y. But I chose this one because I gave this quiz in class, so now I'm doing it in this video. In a typical intro to differential equations class, people would look at this and say, oh, this is separable. This is a separable equation, so I'll solve it as a separable equation. I'm going to divide all the y on this side and then multiply the dx to that side. And that way, all the y's on one side and all the x's on the other side. And I can take integral both sides. Well, for purposes of taking integrals, I'm going to rewrite the left-hand side a little bit. And now I'm going to take the integral. On the left, I have, and on the right, I have x plus c. The 1/3 here and that 1/3 there cancel. I have y to 1/3 equals x plus c. I raise to power third both sides, then the left side becomes just y, and the right side becomes x plus c cubed. Okay, done. Now I apply the initial value. Then on the left, I have 0. On the right, I have 0 plus c cubed. That means c equals 0. And my final answer is y equals x plus 0 cubed, so that's just x cubed. Okay, that's the answer. Let's check. The initial value checks out when x equals 0, y equals 0. Now the equation. If y is x cubed, then y to 2/3 is x cubed to the 2/3. This 3 and that 3 cancel, and I have x squared. So 3y to 2/3 is 3x squared, whereas y prime is equal to, if y is equal to x to the third, then y prime is 3x squared. And that checks out also. Great, we've used the separation of variables method to solve initial value problem, and it looks like the problem is unique. And this is sort of like what a lot of intro students fail to appreciate, is that so many of your homework questions arrive at a unique answer that you would think that it's always the case. Let's check on the uniqueness of the solution to this equation. And for that, we need to know the existence and uniqueness theorems of differential equation of this type, which is what's called an explicit first-order equation. The existence and uniqueness theorems of explicit first-order equations is typically taught in an intro to differential equations class. This is a material that's almost always included. And it goes like this. Suppose we have initial value problem that goes like this. The equation is first order, dy dx is equal to sum f of xy. So what happens is that you're given an equation, it has a y prime in it, maybe many times y prime in it. If you can somehow do legit algebra and isolate y prime on one side, then it's called an explicit first order equation, because it's first order with a y prime, and it's explicit in the sense that we can isolate y prime by itself. The way the existence and uniqueness theorems is taught in an intro class, sometimes the point is not made that clearly, but you really should think of existence and uniqueness as two separate theorems. One theorem for existence and a second theorem for uniqueness. The existence theorem says that if this function f is continuous around this point, then the solution exists near there. The concept of the open rectangle OR is like this. If you have x naught here and y here, then that means that the solution curve, if it exists, would pass through that point. The open rectangle OR is usually described like this. All the points x, y on the plane such that x is between some AB and y is between some CD. So yeah, it's continuous somewhere in there. It may be discontinuous outside of here. It may start being discontinuous out here or up here. But the idea is if we come close enough to the point x naught, y naught, then the f function is going to be nicely continuous near the point x naught, y naught. Okay, that's the idea of an open rectangle on the xy plane. And what it says is that the existence of the solution is guaranteed somewhere near x naught. If you go kind of far away, then all bets are off. That's the existence theorem. The existence theorem guarantees existence of a solution if f is continuous at n near the initial value. The uniqueness theorem adds something on top of it. Well, in order to have a unique solution, the solution has to exist in the first place, right? So it includes the condition that the function f of x, y is continuous. That gets you existence. But on top of that, if you also have the partial derivative df with respect to y, this is just something you need to memorize. Proving it, this one is usually beyond the first course in differential equations, so usually the proof is not included. You just have to remember that it's the partial derivative with respect to y, not with respect to x. And what it says that if the partial derivative is also continuous, then the solution is unique. And we're only talking about the area nearby to x naught, y naught. We're not talking about getting too far from it. That's the existence and uniqueness theorems. And the summary of it is if you have f continuous, then you get existence. If you also get the partial derivative with respect to y is continuous, then you also have, on top of existence, you also have uniqueness. All right, now let's apply it to the equation we have. Here's the form of the equation. Y prime is isolated, so it is explicitly first order. And that means this is the fxy function. fxy is equal to 3y to 2/3. And this is the initial value. The initial point has x naught equals 0, and y naught is also equals 0. So we're looking at the origin. Is f continuous at 0, 0? Well, f is continuous everywhere. This is equivalent to 3 times cube root of y squared. And since it's continuous everywhere, it's continuous at and near 0, 0, and therefore we have existence. We know a solution exists, which is kind of good because, previously we did solve for it. We solved for it as y equals x cubed. But now let's look at uniqueness. For uniqueness, we need the partial derivative with respect to y. Well, it's convenient that the function is only in y. There's no x that appears in it. So taking partial derivative is the same as taking regular derivative. So let's go ahead and do that. and it is equal to 2 times y to negative 1/3. Or is that continuous? Well, let's write in a form that we're familiar with. Now, the 1/3 power means cube root, and the negative means is in the denominator. So 2 divided by cube root of y. Cube root of y is in the denominator, and the initial value is at 0, 0. It is not continuous at 0, 0. Therefore, we are not guaranteed uniqueness. All right, so the theorem says we don't have uniqueness here, but when we try to solve using separation of variables, we did get only one unique answer. So how do we explain that discrepancy? Well, one thing we could say is, well, this theorem is about sufficient condition. If we have this, then we have existence. If we have that, then we have uniqueness. It's not a necessary condition. It is possible to fail the condition and still have uniqueness. Maybe. So we could just like be content with that explanation and stop. But the prudent thing to do is this. If your theory and your practice don't match, at least investigate. So now let's investigate by trying to solve the equation a different way. Let's try solving it using the slope field. Here's our equation. Here's the xy plane. To draw the slope field, we determine the value of the slope at each point on the plane, and then use that to draw the graph. Well, in this case, the slope only changed with y. So we only need to figure out the slope for one value of y and then have it the same for all x values. So let's do something easy first. When y is equal to 0, then y prime is equal to 0. So on the x-axis, the slope is horizontal. Let's try another easy value, y equals 1. When y is equal to 1, then y prime is equal to 3. So let's say here's 1. Then the slope is 3 to 1, like this. And when I have this slope, the rest of the slope on that horizontal line is the same. Now, how about the rest of them? Well, I noticed that this function is an increasing function for positive y. And also, because this is 3 cube root of y squared, the squaring of y means that if you have a negative y, it got squared to be the same as a positive y. So anything on the positive side is exactly the same as the negative side. That means it's symmetric across the x-axis. All of these positive 3 slope on the +1 will also appear in -1. And any slope that is below that will be a little bit smaller. The slope here is 3. And because it's an increasing function, the slope down here is going to be less than 3. So I'll draw something like this. And then the symmetry down here. And something that's above it would be a lot more steep. And symmetry on the negative side Now let's put in our initial value. Our initial value is right there at 0, 0. And you can see the x cubed solution right there. But you can also see that it's not the unique solution. There's also the trivial solution right here on the x-axis. That trivial solution is also a solution. So already we see that there's no uniqueness here. And you may say, okay, it's a trivial solution. Okay, I totally missed that when I was trying to solve the equation. I mean, yeah, plugging in 0 everywhere would work. And I missed that because I didn't think I would get credit for finding the trivial solution. Okay, that's fine. But what I want to show you something even more than the trivial solution. Once you have this trivial solution, you can also have this solution of merging part of the trivial solution with the x cubed. So that makes it a new solution, a third solution already. Well, then you say, okay, well, it's no big deal. You found two solutions, you put bits and pieces of them together, fine. Oh, this example has even more solution. Once I figure out I can just follow the x-axis to get to a new solution, I'm gonna do it again with something like this. I follow along to the point, the initial value, but instead of merging into x cubed, I'm gonna go on a little bit more and then merge. Now it's a totally new solution. You have not seen this before. It's unrelated to the original y equals x cubed. Let's say that that is 2, x minus 2 cubed, but merged with y equals 0. So y equals 0 for x less than 2, and y minus 2 cubed for x greater than equal to 2, like that. And you can see that I can keep on doing this. I can do it anywhere. Not stopping at 2, not stopping at 3. I'm going to pick some weird number way out here, and then I start lifting up. There are infinitely many solutions. A lot of them are something you have not seen before. It's not part of the x cubed. And this obviously matters in real life, because if you need to predict, for example, what is the value of y at x equals 5, then you don't know if it's 0, or it's something at this highlight solution, or something at this yellow highlight solution that is a huge number, or if it's x cubed. 5 cubed is 125. Okay, so we don't know if it's any number between 0 and 125. That's something that we can see by looking at the slope field, but we never could have seen it if we had tried to just solve the equation analytically. So what went wrong? Let's go take a look back at our analytical solution and see why we missed it. This was our solution. What did we miss? Go ahead and look at it again, and maybe hit pause and think about it. This is what we missed. We missed this spot right here. Our initial value is y is of 0 equals 0. That means over here, we divide it by 0. And we're not supposed to divide things by 0. Divide things by 0 messes up. Well, in general, we can sort of ignore that because y is equal to 0 at only one single point. So we can still do the separation of variables and arrive at the general solution. We just have to be really careful about plugging in y equals 0. It's the step of plugging in y equals 0 that gave us this division by 0. And so now we know why this solution is questionable, but you can tell that there's no obvious way. There's no obvious way of going from this solution, separation of variables, plus recognizing that we shouldn't be dividing by 0. And still, how does that get us to a solution like y equals 0 for x less than 2 and y is equal to x minus 2 cubed for x greater than or equal to 2? There's no obvious way of getting there. It's kind of come out of this general solution plus the trivial solution, if we had thought of it, but merging them together to get this piecewise function is not an obvious thing. It only came to us when we were looking at the slope field. So that's my point for this video. The point is the slope field is a lot more important than most students in an intro to differential equations class realize. Any comments or question, please write in the comments section below. Like, share, and subscribe for more contents, and thanks for watching. Bye.